Good afternoon, everybody, and welcome to day 2 of the Cosmological Frontiers and Fundamental Physics Conference. So this afternoon's first session, which I'm going to preside over, is on inflation and its confrontation with the universe. We have 3 speakers. I hope they will not inflate their talks. I'll interrupt them and warn them after 25 minutes with 5 minutes to go. So the first speaker, it's a pleasure to introduce David Poletti on LiteBIRD and testing inflation. David, over to you.
Yeah, thanks a lot for the introduction. I'll do my best to stick to the time. And let me first share my screen. Okay, you should be now able to see my slides, right?
Yes, that's right.
And just in case, I'm full screen, so I don't see any chat or anything. So please interrupt me if you have to tell me anything. Okay, so thanks a lot to the organizers for having me here today. I'm very glad to participate to this online conference. As it was said, I'm Davide Poletti from SISSA, but I was actually a PhD student at APC before moving here, and I'm sorry that this conference is online because it means that I missed the opportunity to visit once more my former lab, which is something I always enjoy very much. And today I will talk about LiteBIRD. I will give an overview of the mission, the updates, and I was also asked to talk in a bit more detail about the problem of foregrounds for this kind of mission. And yeah, so this is what the next 20-25 minutes will be about. And I'm talking about on behalf of a quite large collaboration by now. So the LiteBIRD is a Japan-led mission, but the contribution really comes from all over the world. And we have nearly 300 members of the joint study group that participate to the design and the development of the mission. And the picture you see is the group picture of the last meeting, the winter screen to screen, which unfortunately had to be online as well, but we'll catch up in the next few years, hopefully. And so I presume that many people have heard about LiteBIRD already, but for those who didn't, LiteBIRD will be the next CMB satellite mission. And I say that it will be because in case you missed a couple of years ago, it was selected by JAXA as the next, not the next, but in the program of the strategic large class missions. So if you imagine a torch being passed from one experiment to the other, you had Kobe handed over this torch to WMAP, Planck, and the next CMB satellite mission will be LiteBIRD. And if you don't have this imagination of imagining this torch being passed, we have a picture for you in which Jean-Luc Pouget hands over the torch to Masashi Atsumi. And I swear it's not a Photoshop. It happened. I was there and saw it with my eyes. Anyway, moving on. The main motivation for LiteBIRD is inflation. And I guess I don't have to say much about inflation to this audience. And I'm sure there will be better talks to get into the details of inflation. But let me just say that we all love the inflationary paradigm. At least most of the community likes the inflationary paradigm as it solves many of the Big Bang model limitations. But still, there are many open questions. And we have plenty of theory, but we definitely need more data to constrain this theory and disentangle what's actually the actual reality, what did occur in the primordial universe. And it has very strong implication, not only for cosmology, but also for fundamental physics, because inflation very likely involves something beyond the standard model. At what energy scales, and still an open question. And but we have many predictions, though, from inflationary models. Probably a very important one was the fact that the spectrum of scalar perturbation is nearly scale invariant, and this fact that this nearly not perfectly was actually measured, and this was a great success of the past CMB missions. And another very important prediction is a background of gravitational waves in the primordial universe that should be present also in the moment in which the CMB radiation decoupled from the cosmological plasma and start his path towards the observer. And when in the observations, we are dominated by the scalar perturbations. So, and there's another problem that we have only one CMB to observe. So a way to get better observations and probe this gravitational wave background is to move to a channel that has that is free from the cosmic variance of the scalar perturbations. And since the scalar perturbation has this feature of producing only a gradient type of polarization in the CMB, the B modes, which is the curler-like pattern in the polarization, are a great candidate for probing this gravitational wave background. And and this observable is exactly what LiteBIRD is after. So LiteBIRD that will probe inflation through measuring to very high precision the large angular scales of the CMB polarization, and in particular the B modes that you can see here on the right, together with the temperature and the E modes perturbations. And the requirement is indeed expressed in terms of tensor to scalar ratio. So the way we measure the success of LiteBIRD is really the performances in terms of constraint on the tensor to the amplitude of the tensor perturbations related to the one or to the scalar one. And in particular, the target is a total uncertainty of 10 to the minus 3, which include not only the statistical uncertainty, but also the systematic uncertainty and the margins, observer bias and everything. In case the R turns out to be higher, we will reach 5 sigma detection of the reionization bump at the very large scale, let's say below L equal 10, and at smaller scales, at degree scales, with the recombination bump. So this is what LiteBIRD is designed for, but of course, this kind of instrument has a much, much larger potential science outcome, especially if combined with other probes. And these are only few of the extra science cases that can be done with such an instrument. And I hope to have a few minutes towards the end to get into a bit more details of a couple of them. So probably a question that has to be stressed every time is, why do we need a space mission? So given the the really neck-breaking schedule of ground-based observations from the South Pole, from Atacama, or combined in CMBS4, why do we need a space mission? So these ground-based experiments will do an amazing job in measuring the degree scales and the sub-degree scales, but it will be very, very difficult for them to measure reliably degrees larger than scales degrees scales larger than a few degrees because of the atmosphere, because of the systematics, because of the environment. So the very large angular scale can be obtained only from space. And moreover, space offers also other opportunities, like a completely free choice of frequency bands, which you don't have on the ground because of the atmosphere. And typically these experiments are limited below 300 gigahertz, while in space we can go to higher frequencies. So LiteBIRD will have a resolution of alpha degree at in the middle frequencies, and this means that we'll really complement the ground by providing the larger scale, but we'll also have an overlap that can be used to make sure that the two type of observatories really observe the same thing. As I said, the mission was already selected, and the launch slot was already assigned, and it will be by the end of the decade. There's a bit, so the Japanese fiscal year is not the solar year, but the launch date will be essentially 2029. And yeah, and after the launch, LiteBIRD will fly to the L2 Lagrangian point. So will be located in the anti-sun direction to be protected from the sunlight by the Earth. And it will observe the sky by spinning around this spinning axis. And both sides will design the circles. There will be also a precession of the spin axis. And by the end of 1 year of observation, this is the kind of coverage it will get. It will be fairly homogeneous, which is a really good thing that we like about this coming strategy. And it will have 15 frequency bands, but I will get into this later. So yeah, if you already saw some pictures of LiteBIRD, probably you may be even able to spot a few differences. So we recently changed the configuration of the solar panels, which now have this more regular configuration, more circular, and also the addition of the sun shield. And but the payload, which is composed by 3 telescopes, there are 2 different types of telescopes, a medium and high frequency telescope, which are refractive telescope, fully refractive, and they probe the higher frequency range, and then a low frequency telescope, which has this cross-dragon design. And a common design feature of both types of instrument is the presence of a continuously rotating half-wave plate that helps in mitigating the low frequency noise and the systematic effects. And the focal plane unit are composed of transition edge sensor with 2 types of coupling, a horn coupled detector type and a lenslet coupled detector type. And the key feature of this detector is that they will measure multiple bands in the same focal plane pixel. This is because we need many frequencies, and the surface in the focal plane is very precious. So being able to measure multiple frequencies in the same focal plane pixel is very important to us. There is also, I mean, other important piece of hardware, the whole cooling chain, the readout, in which, by the way, Canada is involved a lot. And but I will try to go more to the foreground part, which was the one I was asked to discuss in a bit more detail. So one of the challenges in this observation lies in the fact that, unfortunately, at this frequency, we don't observe only the CMB, but we also observe emissions from our own galaxy. And there are mainly 2 types of emission in polarization. There are more in temperature, but in polarization, the main emissions are thermal dust, so dust grain, the interstellar medium that gets heated up by starlight and re-emit in the microwave and sub-millimeter frequencies. The emission low is typically a modified black body, as illustrated here, while at low frequency, we are dominated by the synchrotron emission, so cosmic rays spiraling in the magnetic field of the galaxy, and the frequency dependence of this emission is typically this kind of power law. And so you can see that these expressions have an amplitude and also some spectral parameter, which I will refer to very often in the coming slides. And for the analysis I'll show, we have used this reference model in the PySN package, which is based on the Planck dust information, and for the low frequency, it's based on WMAP and Haslam information. So this is the distribution of the 15 frequency bands of LiteBIRD, and the range is so broad because you would really, it's important to us to constrain well these 2 components that are dominated at the low frequencies and at the high frequencies respectively. And so why is it so important is to control the foreground? So to give an idea to those of you that maybe heard about this thing for the first time, or they heard about it, but not in quantitative terms, this is a plot of the angular power spectrum of the foregrounds over 40% of the sky. So if I take the 40 cleanest 40% cleanest sky. This is the spectrum of the foregrounds in at the frequencies of LiteBIRD. And as you can see, there is no frequencies in which we can claim to be foreground free. And actually, we have to suppress this power by quite a large factor. Let's say a factor of 100 in amplitude, which means a factor 10,000 in power. And the way we plan to do that is precisely to exploit the fact that the different components have different emission loads, and that we can use these the knowledge of these emission law, the constraint on these emission laws to get rid of them and unveil the CMB signal. And the fact that these properties may vary across the sky is actually a challenge on the top of the challenge, because if the properties vary across the sky, it means that you cannot use the whole sky to constrain one single set of spectral parameters, for example. So you can see that these are the templates we are using. We can discuss in length whether they are realistic or not, but this is what we wanted to start with as a benchmark. And you can see that spectral parameters vary, and they vary differently depending on the sky areas. And so how do we plan to deal with that? So in LiteBIRD, we actually have many component separation codes available through our many collaborators. Each have different ranges of applications, and but basically all of them have to be pushed to a new level given the high sensitivity requirements of LiteBIRD. So for all of them, some work is needed to be used as component separation codes in the context of LiteBIRD. So there is a huge development ongoing, and the one I will focus on mostly is this last code, FGBuster, which we developed jointly between APC and SISSA in the past few years, in part because it's the one I've involved the most, but also because it is the one that we are using, we are exploiting the most in the evaluation of the performances in terms of tensor to scalar ratio recently. So just to give a primer about the parametric fitting, which is the technique implemented in this code. The idea is that you write your frequency data as a vector, which is equal to the amplitude of your components, which I mentioned a few slides ago, unfolded in the frequency domain by a mixing matrix, which includes the SEDs of the foregrounds and also the CMB. This depends on the spectral parameters, and on the top of everything, you have the frequency noise. And if you know the statistical properties of this frequency noise, you can write this kind of likelihood. And by maximizing this likelihood, you can estimate your sky signal and the spectral parameters. So this is usually done in a two-step approach, which is pretty common to many component separation technique, even not parametric techniques. And the idea is that with a first step, you estimate the non-linear part of the problem, and then you use a closed form solution to estimate the amplitude of the components, including the CMB you're after. And so a big part of the problem, which is the one that I'll focus on the next slides, is how do we choose these parameters? For example, shall we just use a single set of parameters for the whole sky, or shall we use an independent set of parameters for every pixel, or somewhere in between? So, and as I will show now, well, let me show the entire slide then. This choice is very important. Let me illustrate it with this example of a multi-patch approach that was exploited a lot in LiteBIRD until a few years ago. So if you look at the left panel, you see a simulation that includes only dust and synchrotron over 40% of the sky. And in the component separation process, you assume that you have an independent set of spectral parameters over a Hill Peaks pixel of a given inside. So you say you give a maximum resolution to your spectral parameters. So the higher this number, the higher the resolution at which you're fitting the spectral parameters. And as you can see, if this resolution is low, the bias you get is quite high. And this is due to the fact that your sky is more complicated than what your model is capable of accommodating. But this bias goes lower and lower as you increase the resolution of your spectral parameters. So from one end, from one end, you would like to have the highest possible resolution to accommodate as much complexity as possible. But on the other hand, you pay a penalty in terms of noise, and this is illustrated in the in the right plot, in which you basically have two levels in this curve that represent the post-component separation statistical noise power, including like the statistical foreground residuals. So these two levels are basically defined by one upper level, which is the one at which you estimate the spectral parameters, and this other one, which is the one you get when the spectral parameters are given to you, either because you fitted them or because they were just given to you. This noise level is just due to the fact that quadding noisy frequency maps, you get some noise out of this coaddition. So, and the transition between the two levels depends on the scale at which you fitted the spectral parameters. And you can see that the lowest the resolution, the lower the noise, and the sooner this transition happens. And still, we had to do something more refined because we realized that meeting the requirements when the sky was complicated was very, very hard. But we noticed that we have very different requirements on different spectral parameters. So if you let just one of the parameters, for example, the beta of the dust, vary across the sky, this is very similar to the plot I've shown before. But if you do the same thing about the beta of the synchrotron, the biases you get are much smaller. So you have different requirements from different parameters. So we decided to move to a fitting procedure in which we didn't have homogeneous resolution of all the parameters, but every parameter was fitted at the, let's say, the optimal resolution. And this is not conceptually a huge leap, but it does make a difference from the computational and algorithmic point of view, even though I will not get into the details. And the reason is simply that you cannot break the problem anymore into smaller problems. You have to solve everything at once. Okay, so the setup we used included both special resolution for each parameter, but also different for different sky areas. So we divided the sky into 3 resolutions based on the Planck HFI so different sky masks based on the Planck HFI masks. And you can see that you have the best 20%, 20 to 40, 40 to 60, and this is the resolution of the parameter. And you can see that once beta is fitted for at high resolution, we can accommodate lower resolutions for the other 2 parameters we fit for. Of course, we get systematic residuals in the parameters we fit for due to the fact that our model is simpler than what the sky is, but the claim is that that doesn't produce significant and harmful foregrounds residuals after component separation. So this is the preliminary result we got, in which you can see the level of systematic foregrounds we get after component separation. This is measured on a noiseless simulation. While for noisy simulation, this is the statistical post-component separation noise that we get. And in previous slide, you didn't see this rise at the end, and you see it here because in our simulation, we actually have bin effects. So we are paying penalty of the lower bin of the low frequencies. So the larger bin of the low frequencies, but we can actually improve over this with more harmonic oriented methods. And of course, once we have this, we can set constraint on the cosmological parameters. And this is actually a kind of legacy plot. It's not derived from this for reasons that I will tell you in a second. But the idea is that LiteBIRD will be able to improve significantly over the current constraint of Planck and Bicep-Keck, and rule out or detect a large class of inflationary models.
So 5 minutes, Davide.
Great, thank you. So about the path forwards. So we can, something we were working on is to keep optimizing this balance between statistical and systematic residuals, which is really the key. But of course, another direction we are working on is to increase the complexity of the foregrounds, or maybe decreasing it in some respects. But probably the most important thing to mention here is that most of these models are based on information in temperature, and they are extrapolated to polarization. So the really key thing in the next few years would be to get more information about the upcoming experiment that will teach us a lot about the structure of the galaxy, the composition of the grain, and so on. And another thing important to keep doing, we already started, even though I will not discuss, is to consider foreground cleaning not as a standalone problem, but jointly with calibration and the mitigation of systematic effects. And in addition to the few things I was able to show in this presentation, we have actually much more material already, which is part of a comprehensive overview of the LiteBIRD mission that is currently in preparation. And it will include everything from the mission concept to the science outcomes. And so I invite you to stay tuned, and hopefully it will be out in a few months. And as I said at the beginning, I focused on R and B modes just because it's the target, the key requirement of the LiteBIRD mission, but the science case is much wider. And an obvious thing to mention is the fact that given the sensitivity, we'll basically have cosmic variance limited E modes. And so this means in particular that we're able to use the largest scales to constrain the tau parameter, which is a very important thing from the point of view of constraining the reionization, but also has important implication for the constraint of the total mass of the neutrinos, because by comparing the fluctuations, the amplitude of the fluctuations at the last scattering surface and the low redshift measurement, we get this type of degeneracy that we can actually break better if we have an independent measurement of tau. And so of course the science cases can be really rich. For example, we can use the large number of frequency bands to use the Sonayev-Zeldovich effect and map the hot gas in the universe. Another very interesting science case is the one of cosmic birefringence that, for example, we can use to integrate over cosmological distances, exotic models that produce birefringence. Lastly, I'd like to mention that we keep complaining about dust and the foregrounds, but there's a huge science that can be done with this data, and it's very interesting to the galactic science community, and the LiteBIRD will be indeed able to characterize the dust properties and the magnetic field of the galaxy better than Planck did in many areas where Planck didn't have enough signal to noise. So I have to move to the end of the talk, and we're very excited that LiteBIRD was selected as the next CMB mission, and the launch date, of course, as the time scale of a satellite mission, but it's not very far. It's within this decade, and the target is R10 to the -3, including both the statistical and systematic uncertainties, and but the whole science case of LiteBIRD can be much broader, especially if combined with other probes. Foregrounds are one of the key challenges of the mission, and that's why we have 15 frequency bands covering a wide frequency range, and actually extensions of this range are under considerations. We're working also on the component separation technique. I was able to show you a few teasers in this presentation, but stay tuned because we have this comprehensive overview of the mission and outcomes in preparations. Thank you.
So thank you, Davide, for keeping to time. Could people raise hands if they have a question? And as we're waiting, let me just ask you, could you confirm the launch date and the duration of the mission? So
the launch date is basically the end of 2020, and at least at the current stage. About the duration of the mission, the observation time, the nominal observation time is 3 years. So I think that I don't remember exactly the date of the forecasted release of the first result, but it should be something like 2032, something like this, okay, or 2033.
Thanks. Okay, so first, Elias was the first to raise his hand. Could you unmute?
Yes, sorry. Thank you for the very nice talk. I'm not an expert, but I'd like to understand, especially in the foreground story. It seems to me that usually in such cases, especially since you want to see details, you need to understand in very much detail all the processes that can generate the foregrounds. Although sometimes you may have some smart idea, some self-consistency check that can avoid that. Which do you think would go better? Do you really have to understand all of these processes in detail to have a credible signal or not?
In general, as I've emphasized, it will be very important to look very closely at the data that will come from here to the launch of the mission. And by the way, we will have a talk about it right after me. Yeah, we do have the need to understand better for example, the properties of the dust grains. But on the other hand, if we have enough statistical power and we can check whether our data fits well to our model, there's a good confirmation that our model seems to be reasonably good. And of course, there are also other internal checks you can do, like try to do a measurement in an area where the foreground emission is lower, and check that you get statistically consistent results with areas that are more contaminated with foreground. So there are several internal consistency checks that can be done. If foregrounds turn out to be very, very complex, we may need to understand better their physics. So, but the problem is also that, especially in polarization, we don't know yet.
Okay, thank you.
Thank you. Next, Norma.
Thank you. Thank you very much. This mission is very well targeted and technically and scientifically. And so I would like to see much more about the all science implication concerning primary primary objectives, besides, of course, BB modes and error detection, which I think it will be the case. But because precisely have accessibility to low L and to reionization and all the correlation, TE and EE is very important for that. I would like to see much more about running of the spectral index, which will be accessible to this mission, and also to the previous stage of a slow roll for inflation, so-called by now very well known fast roll inflation as preceding that, essentially for low L multiples, inclusive the quadruple, of course, but not only that. So please, what are you? I mean, are you doing on that? Thank you.
Yeah. So I would summarize the question with: are you working on a comprehensive review of the inflationary inflationary science that you can do with LiteBIRD beyond the value of the tensor to scalar ratio? And of course, yes, we're working on it. And beyond this kind of review, there are dedicated working groups being created, and one of them is precisely the inflationary science. So I don't have these extra information to show to you in this presentation, but we are definitely working on it.
Thank you. Next, Subir.
Thank you, Joe. Thanks, David, for a very clear outline of all the issues. I have a very specific question. When you look at the angular power spectrum of the galactic radio background, for example, the Haslam 408 megahertz map, you see that between L of 10 and 100, there is a shortfall below the actual angular power spectrum from a slab of emission. This is how the galactic radio emission is usually modeled in CalProp or something. And Philip Mersch and I showed that this actually is very nicely matched by a contribution from a population of old supernova remnants, which have grown to sub-degree scales. And without this, you can't actually match the angular power spectrum to the few % accuracy that you need. The relevance to your talk is that some of these remnants are very close to us. They look like loops in the radio background. And it turns out, and we showed this with Hao Liu, that these actually correlate with the Planck, SMICA, and NILC maps. In other words, they somehow manage to evade the internal linear combination technique which you described for filtering out the CMB signal from foregrounds. So somehow these old remnants are mimicking a Planck-like, that is to say, black body-like emission over a restricted frequency range. So it seems to me that you therefore have to model the foregrounds and the signal you're looking for simultaneously. You cannot use templates, which, as you said, might be difficult in any case because they might vary from point to point in the sky. And it's a huge task to try to map the sky to that kind of accuracy. But at the very least, you would really need, with a all-sky mission like LiteBIRD, to try and model, jointly model the dust, the synchrotron, and the cosmological signal. May I know what your reaction to that is?
Yeah, well, there are definitely sky areas where the complexity is more than what we've been fitting for in these simulations. And about the specific complexity that you mentioned, I would have to look more carefully about the type of emission that you pointed out and understand whether we can accommodate easily or not in this type of modeling. Otherwise,
well, you say that you are sensitive to R of 0.01. Now, if I remember correctly, that would correspond to about 0.01 micro K. I'm talking about a foreground emission from these loops, which was at the level of 10 micro K, 100 times bigger. Sorry, 1,000 times bigger.
Yeah, okay.
So you understand, I mean, I'm saying that I can believe that with the procedures you are employing, you are able to, understand things and fix them in the way that you described at the few percent level. But it seems to me that to reach R of 0.01, you have to go to sub-percent level. And I find it difficult to understand how that can be done when the foregrounds are, as you acknowledged, not uniform over the sky. So for example, a nearby object, which happens to be accidentally close to us, subtends a large angle, comes out at high galactic latitude. So the usual mass, etc., are ineffective against those things because they are, at high latitudes in the sky. In that case, you really need to attack the problem not in a stepwise or factorizable manner, but simultaneously you must fix the foreground and the signal because it will vary from point to point in the sky. So I find that, look, we all agree it's a difficult problem and you're clearly trying to do your best, so please don't misunderstand me. I'm just trying to understand where your claim that you can see R of 0.01 at 5 sigma comes from. I frankly cannot see that.
So,
okay. Sorry, one very brief comment on that, if you like, Davide.
Yes.
Yeah, so something I can say is that there are definitely complexities that were not in these simulations. And the idea for the future is that we definitely need other type of traces to, for example, correlate with the CMB map, just like the analysis you mentioned about the correlation with the SMICA maps. And but one of the reasons why we want to have a wide range of frequencies is precisely because we would like to be able to detect if there is something that our model is not capturing. So maybe we are getting an estimation with a simpler model, but our goodness of it might be able to tell us that there's something going on in that region, and maybe we are able to isolate it and to exclude it from the cosmological analysis. But yeah, I agree, it's a challenge, but that's why it's so important to have also other traces, possibly independent traces, to maybe correlate with the CMB maps that we will produce. Okay, I think we are running out of time, so I'll hand over.
Yeah.
Thank you,
Davide, for a very illuminating talk. So now we must move on. It's inflation again and dust foregrounds this time.